right, good morning. We are recording. We are doing, let's see, what are we doing now? We are doing 2017 questions 1 and 2 today. I hope everybody had a great spring break. Hope everybody was able to do 2016 at their own pace and just kind of relax a little bit. I'll be taking that up next week. Just a reminder of how grades are working. Remember that your final grade for this semester is going to be your Q3 grade plus 10 points, all right, if you do 100% of the assignments. And so, I mean, I don't know how many assignments we're going to have. We're going to have all the years, so you should be turning in 2014 and 15 this week, turn in 2016 and 17 next week. The manual will also be included in that, but that'll be kind of what we're going to be doing after the AP exam, and we'll talk more about that later. Just still trying to get a bunch of moving parts together, but anyway, if you have any questions about anything with the grades, just let me know. Just be submitting everything to my email, and I'll be keeping track of that. All right? All right, let's go to number one. Number one, it says that a tank has a height of 10 feet. All right. And the area of the horizontal cross-section of the tank at height h feet is given by the function a, where a of h is measured in square feet. Okay, so the function a is continuous and decreases. All right, so let's go ahead and start making some notes here. All right, a is continuous and decreases as h increases. Selected values of a of h are given in the table above. All right, so A of H is the horizontal cross section of this tank as the height's increasing. So I try to draw this out just so I can kind of have a visual here of what's going on. So like we got this tank, right? This tank it's 10 feet tall, okay? And if I take a horizontal cross section at 0, 2, 5, or 10, these are what the areas of that are going to be, right? So the cross-sectional areas are getting smaller and smaller. So I don't know what the base looks like. I don't know if it's a consistent base here, but I just kind of made like some type of like squarish type shape. And as we increase in height, so does my cross-sectional area. Okay. So the tank looks something like that, right? Like here at 0 feet, like this area right here, this base is 50.3 in area. And as we increase, as we get all the way up to 10 feet tall, it has an area of 2.9. And so the areas are decreasing as we go. So I'm picturing some type of like conical looking shape almost, okay? Or some prism, some pyramid type shape maybe, okay? So anyway, just so you kind of have an idea of what it looks like, okay? This area was 50.3. Here, like at a height of 2, for instance, this area right here, this cross-sectional area is 14.4. Okay, so I think that's good to maybe think about. And part A says use a left Riemann sum. All right. So, So we're using a left Riemann sum with 3 subintervals, okay, which works out because there's 1, 2, 3. Indicated by the data in the table to approximate the volume of the tank and indicate units of measurement. All right, so if I do Riemann sum, it's going to be adding up all these values. It's approximating the integral, right? And what the integral is doing is it's adding up all of these cross-sectional areas, and if I add them all the way up from 0 feet to 10 feet, we're going to have the volume of this figure approximately, okay? So remember that Riemann sum approximates integrals. So this is saying the integration from 0 to 10 of a of h dh. Okay, that's what Riemann sum is finding, and that's approximating by doing areas of these 3 rectangles, and that will be approximating the volume, right? So we're doing left Riemann sum, so we're going to start with the leftmost value. And that value is 50.3, and then times the base, which is from 0 to 2 is a length of 2, plus 14.4 times the length of the base is 3, and then plus 6.5, and then times the base is going to be 5. Okay. And this is a Calc active problem, so if you type that in the calculator, I got 176.3 volume is feet cubed. Okay, so there you have it. That is the left Riemann sum. We've done that a bunch of times with charts. Just think it was an interesting problem that we were doing. It's representing cross-sectional area. So there you have it. That is A. All right, B. B says, does the approximation in part A, all right, so that value, that approximation of the volume, is it an overestimate or an underestimate of the volume of the tank, and explain your reasoning. All right, we've talked about, we know what Riemann sum left and right does with increasing and decreasing functions. We talked about that combination numerous times, right? This function is ultimately decreasing, right? So if I were to take these x and y values and put them on like an x and y coordinate plane, okay, looks something like this, right? It is a decreasing function of values. So if I do a left Riemann sum, what does a left Riemann sum do with a decreasing function? Well, it's an overestimate. So we overestimated the volume. And as far as your explanation goes, it's just literally saying, like, it's just combining the fact that you know left Riemann sum is an over-approximating for decreasing functions. So you're going to say overestimate because left Riemann is an overestimate of decreasing functions. And that's just a definition. So you're good with just putting that. All right, let's go on that. All right, let's go on to part C. It says the area in square feet of the horizontal cross section of h feet is modeled by the function given by f of h. All right, so normally we were given a chart. We were saying, all right, here's the chart that approximates the value. But now we're saying, all right, forget the chart. Now I'm saying at any given time between 0 and 10, this function is going to tell me the cross-sectional volume at any given time at 0 all the way to 10. So we don't have approximation anymore. We actually have a function. So it says based on this model, find the volume of the tank. Okay, we're finding the volume of the tank, the same thing that we estimated in part A. Well, we no longer have to estimate because we actually have a function for the cross-sectional area. So all we literally have to do is take the integral, and we can actually do it now. There's no approximation. So what this looks like is it's going to be the integral 0 to 10 of f of h dh. So that function there. And all you have to do is type that in the calculator exactly like you see it. Okay. And honestly, guys, I put this in for y1 in my calculator. So in my calculator, I just did the integral 0 to 10 of y1 and dx. Okay, that's all I did in my calculator. And I got 101.3253382. Okay, so that is the actual area. That's the actual area of the tank from 0 to 10. Now remember what we found in A, it was 176, which we determined in B was an overestimate, right? Because that's definitely bigger than the actual value. Okay, so hopefully all three of those answers should be lining up there. Oh, indicate units of measurement. This is volume again, so that's going to be feet cubed. Okay. All right, any questions on that? Yeah, all right, cool. Let's keep going. And then D. D says water is now pumped into this tank. So imagine that little pyramid tank I drew in A being pumped full of water. When the height of the water is at 5, so in the middle there, the height is increasing at a rate. So, okay, let's just stop right here. It says when h is equal to 5, the height is increasing at a rate of 0.26 feet per minute, foot per minute. So that value is dh over dt. It's telling you the rate at which the height is changing. So let's make note of that. So using the model from part C, find the rate at which the volume of the water is changing with respect to time when the height is 5 and indicate units of measurement. So what it wants us to find is dv over dt. That's what it wants us to find. So in order to find dV over dt, I need to have an expression for volume. So I can take the derivative and solve for dV over dt. Well, what is my expression for volume? My expression for volume is the integral of this, like I found in C. It's going to be the integral 0 to h, because this is depending on what the height of the water is, right? Of f of h, which I'm actually going to write out what f of h is. I'm going to say of 50.3 over e to the 0.2 h plus h dh. Okay, that's my expression for volume. Okay, if that's my expression for volume, because it's just an accumulation of all the cross sections, all the way up to any height, so that tells me my volume. Then what is dV over dt? What is the derivative of this? Oh, and I apologize. If I'm writing an expression, like remember how we said this, and I've told you this many of times, if I make this h, I can't make the same variable in the integral also h. So we're going to make that, I apologize, we're going to make this x right here. Right? That way, because it plugs in h, I can't have the same variable in the integral and the function. We've done that plenty of times. So then that means that dV over dt is equal to, how do I take the derivative of an integral? Well, remember by FTC part 1, it's just plugging h in for x. So this is going to be 50.3 over e to the 0.2 h plus h. But remember that this is implicit differentiation. I'm taking the derivative with respect to time. So if I'm taking the derivative of h, that's going to be times dh over dt, right? That's just chain rule, right? Plug in h and then times the derivative of h is dh over dt. So this is the expression for my dV over dt. Now, if I want to know what that value is at h equals 5, then I just plug 5 in for h, and I'm going to plug in 0.26 for dH over dt, and I got my answer. And again, I did all this in the calculator. I actually still have this in as y1, so I did y1 of 5 times 0.26. So dV over dt in my calculator, what I typed in was y1 of 5, and then times 0.26. And when I did that, I got the answer 1.694418,562. All right, so that wasn't a terrible problem, I don't think. D maybe sound a little bit confusing, but you just had to know what your expression for V was in order to find dV over dt. Okay. All right, let's look at the answers. Oops. All right, so, ooh, look at this. I might have messed this up. I did. I didn't put the units of measurement in D. Let's see, we're talking about indicate the units of measurement. So this is a rate, which if you look, the rate of change is going to be its volume changing per minute. So that's cubic feet per minute. You see it right here, or feet cubed per minute. So this is feet cubed per minute. My bad, I forgot to put that. So if you look at the answer key, you get 1 point out of the whole 9 points for making sure that you have units in part A, C, and D. Correct units in A, C, and D. So hopefully I did that in all the video. I think I did. But anyway, in part A, we did left Riemann sum correctly, and we got the correct approximation. We said overestimate with a reason. In part C, we got the integral right. That was just the integral of the expression they gave us, and got the answer. So I think A through C were pretty doable. And then D might have been a little confusing, but it was 2 points for finding dV over dt, which they used the notation. I actually just, I guess I said that, but they didn't write out the full derivative like I did. They just wrote it as dV over dH, but we wrote the whole thing out. It's fine. And then a point for the answer, which was 1.694 cubic feet or feet cubed per minute. Yeah, okay, so that was 2017 number 1. Let's go on to number 2. All right, Number two. Number two is a polar area. Now remember, polar area is taken off of the AP exam this year, so if you didn't do it, not the biggest deal in the world, but as far as grade goes for this class, I would like to see some notes on this, maybe your attempt as well as maybe some type of corrections. All right, I think you still should attempt it, or at least just write down my notes for credit. Okay, so let's do number two. Number two, I think this was a good problem. It wasn't bad. Okay. Now, honestly, guys, like I know this is a polar equation, but and this is Calc active, but I left my calculator in rectangular mode the whole time, and I just did it that way, and you'll kind of see that's just as helpful. So, all right, it says the figure above shows the polar curves of r equals f of theta, which equals 1 plus sine theta cosine 2 theta. If you were to graph these, you would see that it's this function here. And we should also know that 2 cosine theta, we know that's a rose with one petal there. We know that's this function right here, okay? And that's between 0 and pi over 2. So we're here in the first quadrant for both of those, okay? Now it says let R be the region in the first quadrant bounded by the curve f of theta, which we see is this function right here, and the x-axis. And S is the region between the two functions in the first quadrant. Okay, so we got all this information here at the beginning. A says find the area of R. All right, this is not bad. A is usually not bad with these. Okay. If I'm finding the area of R, remember it's all based off of a sweeping motion of the radiuses from the origin, and it's going to be going from a theta value of 0 all the way up to a theta value of pi over 2, and it's a sweeping motion. So how do you represent area with that sweeping motion polar? Remember, area is equal to 1/2 integral a to b of our r function squared. All right, so simply put, in this function here, the area of r is going to be the integral, or 1/2, sorry, the integral 0 to pi over 2, all right, my bounds there, of my r equation, which in this case is that equation. So I'm just going to write f of theta squared d theta. And that's all that I did. Now, in my calculator, I kept this in rectangular. I put f of theta as y1, and I put g of theta as y2, and I kept those in there the entire problem. So in my calculator, literally all I did was 1/2 the integral 0 to pi over 2 of y1 squared d theta. Okay. And what I got was 0.648414379. All right, not too bad. Yeah. All right. Now B. I love this problem. It says the ray theta equals k. Now remember, theta is just an angle from the origin. So I'm going to go ahead and draw k. There's k. Okay, that could be theta equals pi over 6, or theta equals pi over 3. There's some theta value between 0 and pi over 2 on this curve. That's going to divide S into two regions of equal area. So I'm saying this line right here said that this area and this area are equivalent. So those are equal. Now I want us to write, but do not solve, an equation involving one or more integrals whose solution gives us the value of k. Now the answer key has two different ways. I'll show you the way I did it, and then we'll discuss the other way when we get to the answer key. This is how I thought about it. Well, first I wanted to know, because we've done this with just regular rectangular area in the past, I want to know what the area of the entire region of S is. That's not too bad. Remember, that's a sweeping motion from 0 all the way up to pi over 2. Now, if I did it for just this outer equation, It's going to give me this entire thing. Well, how do I get rid of the area of R? Well, I'm going to subtract out the area of R, right? So remember how this works. It's going to be the sweeping motion of the outer function minus the sweeping motion of the smaller function. So all of s is equal to 1/2 integral 0 to pi over 2, okay, integral 0 to pi over 2 of my outside function, which is going to be g theta squared. Now that's going to give me not just the region S, it's going to give me the whole thing. So I'm going to subtract off the region of R, which was f of theta squared. Okay, so that right there, that gives us the entire region of S. Okay, now how do I solve for K? Well, I'm going to set this equal to. I'm going to say, all right, well, how I find K is going to be equal to half of that. So I'm going to say, all right, half. All right, I'm going to say half of some integral is going to be equal to the whole thing. So if I take half of, all right, well, no, I said that backwards. I apologize. I just realized I said that backwards. If I take half of this, all right, if I take half of the entire area of S, right, it's going to be equal to some integral with K, right? So if I take half of this, it's going to be the integral, all right, of 0 to K, and I should say 1/2 because that's how area works, of g of theta squared minus f of theta squared. So if I take half of the entire area, it's going to be equal to some area from 0 to K. Does that make sense? Do we see kind of what I'm talking about there? Now, in the answer key, they simplified out the 1/2 and the 1/2, and they left it like without the 1/2s. But I just left the 1/2s in my answer to just make sure we understood what was going on. But I want us to understand that in this red bracket here is the area of the entire S, and half of that is going to be equal to the area from 0 to K. All right, so there you go. All right, now let's go on to C. C says for each theta value between 0 and pi over 2, we're going to let W of theta be the distance between the points of the curve from my F equation and my G equation. Let's write an expression for that. So W of theta represents, so if I'm doing theta, like, let's say I'm going to draw theta all the way around. Here's theta all the way around, okay? Now W of theta is just the distance between my function G of theta and F of theta. It's all of those in red. Well, how do I take that? How do I figure that out in terms of theta? Well, it's just going to be this value, subtract this value, and I have that distance. So literally, W of theta is equal to the difference in my outside function and my inside function. That's what W of theta is. It's just, that's the distance, right? That's the difference between the two, okay? So, knowing that, I wrote my expression for W of theta. I got to check there. Find the average of W over the interval 0 to pi over 2. It wants me to find the average distance between the two functions. We know what average is equal to. 1 over b minus a times the integral of the function of whatever the function is, which in this case is W. So simply put, it's going to be 1 over, all right, pi over 2 minus 0 integral 0 to pi over 2 of W of theta, d theta, okay? Which, when I did this in my calculator, exactly how I wrote it, and I think you should get good at writing it exactly as you write it on your paper, I did 1 over pi over 2 minus 0 times the integral of 0 pi over 2. Remember, I made the G equation y2, and I made the f equation y1. So in my calculator, I did y2 minus y1 to represent w of theta dx. And in my calculator, I got 0.485446135. Okay. So there you go. That is the average value of the distance between the two functions. Okay. Cool. And then lastly here in part D, it says using the information from part C, so that w of theta information, find the value of theta for which w of theta equals the average w of a. So it wants me to first of all figure out when, it wants to know when w of theta equals the average, which remember the average was 0.485446135. Okay, so I found this intersection in the calculator. It's actually kind of an interesting way I did this. I want to see if y'all can see this on my screen here. So on my screen, like I typed in y1, I typed in y2, but look what I typed into y3. I typed in the difference of y2 minus y1. So I literally wrote in w of theta in for y3 there, if you can see that on my screen, by taking y2 minus y1. And then I made it to where my graphing calculator did not graph y1 or y2. And you can do that by highlighting the equal sign beside y1 and y2 and unhighlighting it. So like you see how y1 and y2 are unhighlighted, but y3 is now highlighted. I thought that's kind of interesting. So then I graphed 0.485 whatever into the calculator. And then when I graphed it, I did zoom fit. And now it's not going to do it for me. I did a zoom fit. And I hope it does it for me now. I messed it up. But anyway, because second insert 1 plus. So it's graphing it. Oh, I messed up the because I turned them back on. Dadgummit. Anyway, I found that intersection in the calculator, which was pretty cool. And it ended up being theta equals 0.5176879. 0.517687795. And then it wanted me to figure out, okay, so then it says, is the function w of theta, which was y2 minus y1, or the difference of the two functions, it wanted to know if it was increasing or decreasing at this value and give a reason. So simply put, all we have to do is figure out w prime of 0.517687795. If it's positive, it's increasing. If it's negative, it's decreasing. That's just derivatives, right? So when I typed this into my calculator, I did like when you did the derivative on the calculator, I did d over dx of y2 minus y1 evaluated at 0.517687795. And I got that value to be negative 0.581 something, 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 which is less than 0. So therefore, w theta is decreasing. So there you have it. I mean, that's not too bad. Fun little problem there. Just a lot of it was done in the calculator. It's just pretty much being able to set it up and do it in the calculator. So looking at our answer key here, we got, for A, we got the correct integral and the correct answer. So you can see those right there. Now, here's B. The B expression that we came up with, we did this one right here. Remember I said they simplified out those 1/2s? So this is what we got. Look at what they did. And some of y'all might have done this on your own. They simply just said, well, hey, do one integral from 0 to k, and that's going to be equivalent to the other integral from k to pi over 2. Like from 1 to k and then 0 to k and k to pi over 2, those are going to be equal areas. Like, well, that's another good way to do it. But I chose the first way. We got a point for doing g of theta minus f of theta, a point for doing the correct average value, and then getting the correct answer. We solved for where it equals the average in the calculator, and then we gave an answer for why it was decreasing, because the derivative was negative. All right, so that was questions 1 and 2. We'll do 3 and 4 tomorrow. Good luck. I tried to keep it right at 30, and I kind of did. I'm going to end it.